and see what happens. Um, but anyway, so just so that we're all on the same page, we're all here to learn about the effect of finite size artifacts on binding free energy calculations of charged compounds um, uh, done or calculated from simulations using periodic boundary conditions with Ewald sum, like particle mesh Ewald or other Ewald sum for long range electrostatics. Yes, that's what you all wanted to hear about, right?
Everybody just ran away.
Everybody just ran away. Well, I don't blame them.
Yeah, that's exactly what we wanted.
Okay. Okay. So let me just apologize to begin with. This is a part of my PhD work, which is about 3 years old at this point, and I'm doing pretty different things right now. So you'll have to bear. So I've gone over this to make sure that it's all somewhat fresh, but bear with me because I'm putting this back into my head for the first time in a while also. So yeah, so binding free energy calculations of charged compounds. So the basic, well, I'm going to tell you about, I'm going to organize this into 3 different pieces. I'm going to start by telling you some, like, the major important difference in terms of electrostatics between periodic and non-periodic boundary calculations, and then an overview of the correction terms that we worked out in this 2013 Chem Phys paper that I encourage everyone to read. And finally, the results of the simulations that show that these correction terms are useful and accurate. Okay, so periodic versus non-periodic calculations. So the basic difference, at least the easiest way to understand the difference in terms of electrostatics is the way that periodic and non-periodic calculations define zero potential. So imagine that you have a point charge in a system that's modeled as non-periodic. So that point charge is creating an electrostatic potential that's very strong near the charge, and then it decays as you go farther and farther away. And finally, infinitely far away from that charge, you could say that that's where you have zero potential. Now, in a periodic system, obviously there's no such thing as infinitely far away from the charge. So the convention that's used and what makes the math work out is to say that zero potential is the average potential in the entire unit cell. So the way that I've colored this is there's some potential created by the positive charge that I'm drawing as blue in like close to the positive charge, and then farther away from it, the potential turns red because if you integrate the potential over this entire square here, it needs to add up to 0. So if there's going to be a strong positive potential near the charge, then there needs to be some negative potential far away, so that the average of the entire thing is 0. So this is different from the non-periodic case where there's no constraint on the average potential. Okay, so a way to understand what happens when you take your intuition about what's going on in a non-periodic system and move that over to the periodic system is to say that the potential at some point in the periodic system is approximately equal to the potential that you would see in a non-periodic system plus some uniform offsetting potential. So the idea of the uniform offsetting potential is that if you add this kind of light shade of pink on the right to the spatially varying potential that's caused by the charge, then the sum of these two would add up to 0, and they would give you your 0 average potential, which is the constraint of the system that's drawn on the left. So if you could calculate your non-periodic potential, then you know what the offset potential has to be in order to give the potential in the system on the left, which is going to be average 0 over the entire thing. Is someone asking me a question? No. Okay. I'm gonna click another. Well, it seems okay. Whatever. Yeah. Please stop me at any time if you have questions. Although you might have to get close to a microphone.
I have a question. Can you hear me?
Yes.
Um, you have an approximation sign. Like, where does, like, is it, like, when is it, like, a good approximation or a bad approximation? Is it, like, a really good approximation or what?
Yeah, that's a good question. Um, I think, well, the reason why I've drawn it as an approximation is that, like, the non-periodic potential that I've drawn doesn't really exist because there is no, like, you can't take your periodic system and say, well, this is what your periodic system is if it were non-periodic, because that's a different system. So 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 you're going to use some kind of approximation to say, well, this is like approximately what a non-periodic system would look like. So, for example, for a single charge, like for the thing that I've drawn here, which is a single point charge surrounded by some continuum, whether that continuum is vacuum or whether that continuum is like water, then that approximation is going to be basically exact, because it's easy, because you can model water as a continuum very accurately with Poisson-Boltzmann, and that's easy to go back and forth between that continuum water in a non-periodic system and that continuum water in a periodic system. But as your system gets more complex, you can't go back and forth as easily, or you can't approximate one by the other. Okay, so I don't have a good answer to your question about when it's a good approximation or not, but I can show you how useful it has been to make that approximation in terms of comparing results to our MD calculations later on in the talk.
Okay, thanks.
Is that satisfactory?
Yeah.
Okay. So going forward, the next question is, okay, if your periodic potential is like your non-periodic potential plus some offset, one of our goals in understanding this and correcting for it is to figure out, okay, what are the things that are creating offset potentials? And the answer to that is anything that changes the average potential in your periodic unit cell is going to induce some kind of offset potential. So what are the different factors in your system that can change the average potential in your unit cell? So there's a few of them. So first is like a bare charge. So if you have some charge that's not neutralized by something else, then it's creating some potential across your entire unit cell. So that's changing the average potential in the unit cell, and it's going to induce some kind of offset potential. Now, there's another thing that can change the average potential in your unit cell besides just a bare charge, and that's what other people have called an isotropic quadrupole. So the definition of an isotropic quadrupole is some point charge at the center surrounded by a sphere where the charges on the surface of the sphere exactly neutralize the point charge at the center. So the funny thing about an isotropic quadrupole is that outside of it, there's no change in the average potential. This creates no potential outside the outer sphere. But inside the sphere, there's some average positive potential. So the average potential in the unit cell as a whole is changed because of the potential inside this volume of the sphere, even though if you're outside the sphere, you don't feel any potential attraction or repulsion or whatever because it's all totally neutralizing itself. So does everyone see how there is some average potential in the system due to this isotropic quadrupole, even though outside of itself it's not creating any electrostatic effects? Okay.
Yeah.
Okay. So the next thing to see about this isotropic quadrupole is this is basically what a water molecule looks like. There's some charge at the center and then some charge on the outside, and because the two are neutral, like on average, there's some dipole, right? But on average, it doesn't change. It doesn't create an average potential outside of itself because it's neutral. But inside the water molecule, there's actually a negative potential caused by the central oxygen atom, and this actually makes a difference in the absolute average potential of your system, and is one of the things that creates an offsetting potential that needs to be accounted for. So besides just a water molecule, oh, actually, uh, yeah, let me just make this point, which is that if we have these two different things, the potential caused by this bare charge depends on the system size, because there's more volume. There's more volume. Like in a non-periodic, if you imagine you were just integrating out to some cutoff, the farther out you integrate, you're integrating more of the potential of this positive charge. In the case of the isotropic quadrupole, you can, once you have integrated the potential past the outer spherical boundary, it's not changing anymore. So the potential created by this isotropic quadrupole is constant as the volume grows. However, if you fill your box with water molecules, you're adding more and more of these isotropic quadrupoles as your box gets larger and larger. So these two have interesting and different dependencies on the volume of the box. Okay, so I already talked about water molecules. Another thing that was not recognized before we did this work was that besides water molecules, your protein can also, even if your protein has no net charge, it can also have some average potential, which can be analogous to an isotropic quadrupole. So, you know, different proteins will have different charge distributions. Sometimes they have some set of I'll just leave it at that. Different proteins have different charge distributions, so you can't predict, you know, all proteins won't affect the average potential in the unit cell in the same way, and it's something that should be, you know, numerically computed for each protein, and I'll talk more about that later on. Do we have any questions right here, or should I keep going? All right. So you can get changes in the average potential in your unit cell due to bare charges, due to water molecules, and due to your protein. Okay, so now I'll show you the correction terms that we introduced to calculate these effects and how you apply them to your MD simulations. So there's 4 different finite size artifacts that will affect charge binding free energy calculations. 3 of them. Let me pause and define what I mean by a finite size artifact. So you run some periodic simulation, which gives you a result that is correct for the periodic system that you're simulating. But the periodic system that you're simulating probably has some arbitrary parameters in it, like the unit cell that you built was picked for computational convenience and has nothing to do with any like realistic concentration, and it's going to be arbitrarily different from what other people are simulating. So what you'd like to do is take your periodic simulation and extrapolate the results to some meaningful reference state that could be compared between different groups or compared to experiment. And the meaningful reference state that we argue for in this paper is the idea of an infinite non-periodic system where your molecules are at infinite dilution. You know, when you do your experiment, obviously there are non-idealities and your molecules are at some real concentration, which is not just like one molecule in infinity of water. And sure, those non-idealities exist, but if you want to capture them, the right way to capture them would probably not be to try, like, those non-idealities are different from non-idealities involved that occur from representing your system as an infinite periodic lattice. So the question of the difference between an infinite periodic lattice and a single molecule in a non-periodic system with infinite volume of water around it is different from the non-idealities between that infinite dilution situation and your experimental situation of that's not periodic but has some actual concentration. So when I say finite size artifacts in this talk, I'm talking about how to go from your simulation results in some periodic lattice to what those binding affinities or other quantities would have been if you had simulated them in a non-periodic system with infinite solvents surrounding your one solute molecule. And then at least that's a consistent reference state that anyone who's doing simulations or other calculations can use to compare between each other. And it's probably a good reference, or is at least better than anything else, to compare between a simulation result and an experiment. Okay, hopefully that made sense. Okay, so how do you go from your quantity calculated in your periodic boundary lattice to what that quantity would be in an infinite non-periodic system? Well, first you have to correct for these three potential offsets. One offset to the average potential caused by the net charge on the solute, an offset caused by the solvent, both because of the average potential that solvent creates and because of the potential inside each solvent molecule because of that isotropic quadrupole effect. Sorry, is someone trying to ask a question? No. Okay. And also, you have to correct for offsets caused by the term that we introduced is the residual integrated potential. So this is the change in the average potential caused by factors that are not net charges or solvents. So this is a catch-all term for anything else. But in terms of protein binding calculations, the main contributor to the residual, what we're calling this residual integrated potential, is the protein itself, and it's the protein's effect on the average potential in the unit cell caused by the fact that it has some weird charge distribution and the fact that the protein has some excluded volume. Both of these two things affect the average potential in the unit cell, inducing some offset potential that needs to be corrected for. And then the final finite size effect doesn't relate to offset potentials, but it's this idea of undersolvation. That, for example, if you have an ion in a periodic box of water, there's a fixed amount of water that is solvating that ion that's creating a favorable potential at the location where the ion is. But if you had an infinite system, there would be more water creating some even stronger potential at the location where the ion is. So this undersolvation effect is just the difference between the solvation that you get from the limited amount of water in your periodic system versus the infinite amount of water per ion that you have in an infinite system. Okay, so we're going to calculate some correction term for each of these four different things. So the basic way to correct for these effects is to remove, or at least the first three effects, is to remove the offset potential, which was created by all these different things that change the average potential. So you need to calculate the average potential in the unit cell. That's this integral of phi dv. And then to get the average potential, you can divide that integrated potential by the volume, and that offset potential is what your ion or your ligand or whatever is being perturbed, is feeling, is experiencing, that's different from what it would feel in a infinite non-periodic system. So So this this 1 over volume, the integral of the potential over the volume is what we're calculating in each of these different cases, and then subtracting the effect of that offset potential. So let me give an example that actually uses signs that might clarify this, because I've been being a little lax with plus and minus signs. So let's say you have a positive charge in the center of your box. It creates a potential over the entire box that repels other positive charges. But because of that, because the average potential in the box is positive, to keep the average potential 0, because this is a periodic calculation, there's some negative offsetting potential that's introduced in the periodic calculation, and then that positive charge at the center feels that negative offsetting potential and is, you could say it's attracted to it, but the point is its energy is actually favorable because that positive charge is interacting with the offsetting potential created by its own, which is the response to its own effect on the average potential in the unit cell. So basically, if all of you go to your GROMACS or whatever your simulation system is that does periodic boundary calculations, and you just put one ion in a system, you'll see that that ion has some favorable energy because it's interacting with the response to its average potential.
Hey, Dave, this is Mike.
Yes.
Does it affect forces?
It
looks like it doesn't if you assume it's a fixed offset.
I don't have a good answer to that because I didn't look at it in great detail. But so for it to affect forces, the potential would have to be different depending on something about the configurations. Yeah.
Well, well, it would have to be space varying, is what it would have to be.
Yeah. Right. So
and your model is that it's not space varying, right?
Can you guys hear me?
Yes.
Okay. So I think it doesn't vary in space for a fixed configuration, but if you imagine a conformation of a protein changing so that it changed the quadrupole moment or something, then you can imagine it being configuration dependent.
Right. Yeah. It would be configuration dependent, but at any instant it wouldn't generate a force because you're not figuring out how that change in potential configuration affects.
Yeah.
It goes into the gradient, right?
Yeah.
So that's good, right? So at least your simulations, in some sense, are valid in this program.
Yeah, I'm not sure, but you want more, like, for example, the quantities that we're interested in that we're often interested in are free energies. So if some configurations are favored and some configurations are disfavored, then that's bad.
Well, I can see that if you're doing FEP where the energies go into it, or if you're doing entropy calculations where the energies go into it, it's a problem. But it seems like if you're doing TI, all you ever compute is forces, and you may be okay.
I don't quite understand what you mean by the difference between by why it would affect FEP and TI differently.
Well, because in TI, you compute the average force on something effectively along lambda, and then you integrate over distance, so you get a work integral, which is the free energy difference. Whereas in FEP, you actually have to compute energies of configuration. So they're usually just spring energies, so in that case, it may not matter either, actually.
Well,
it's a static energy vector. If you're doing a charging integral of FEP, you may have trouble. Right?
Say for example, you were doing a PMF calculation of pulling an ion out of a binding site.
Right.
And of pulling an ion out of a binding site, you would, if the configurations on one end of that calculation or another are energetically favored, then you're going to have an artifact in that calculation.
Not if the energy difference never manifests in a force, because if all you ever compute is a force, then there's no mechanism with the manifest. Although I certainly see what you mean that you end up with an inconsistency.
Okay. We should think about this more, but in general, well, okay. Since they're computing the same free energy, I would have thought that the FEP calculation and the TI calculation would have to give the same result.
And I think it'll still be okay because the energies that are getting perturbed in what you're talking about are electrostatic energies. But if your FEP doesn't involve a charge change step, if it's only like a pulling calculation where you've got a spring, the energy that shows up in the formula is the spring energy. You never see the electrostatic energy show up. So in that case, it should be okay. Now, if you did TI on a charging process, I can certainly see how TI and FEP should then give discrepant results in this.
Wouldn't the fact, like in your spring calculation, the spring is I mean, wouldn't the fact that configurations on one end of that spring are energetically favored compared to what they would be in a non-periodic system?
No, but I don't think so. But no, they won't affect the spring because unless, but basically, let's say I take a system of charges and springs, okay, and I compute the force in some configuration. I then take the whole thing and put it in a lab, in a laboratory, which is where I can generate a uniform electrostatic field everywhere in the system. None of the forces will change. And I can ramp that thing up and down, and it'll have no effect on the dynamics or on the free energy difference. So it's like the whole free energy difference is, you know what I'm saying?
Yeah, there's another issue though. So it could actually depend on the details of the analysis. So I've done PMF calculations where I've actually used like the spring energy, but I've also done them where I've used the total potential energy and subtracted the total potential energy for a different nearby configuration in order to get what I thought was the spring energy.
Right.
But in that case, I could be picking up something else that I didn't think I had.
Right.
I think the question relates to how are the forces computed within the Ewald framework, because you're still like the numbers that you're getting for how strong those forces are have an electrostatic component, and I don't know the details of how forces are computed under PME.
Right. So yeah, because this is something that can certainly be tested empirically. But my guess is that, I mean, in order for that dependency that you're talking about to manifest in the forces we're talking about, like a spring force or whatever, I mean, essentially you're saying if that were the case, then you're saying that not only do we have to do energy corrections, we have to do force corrections everywhere, which I don't think is what you've been claiming. I mean, that would be a lot more complicated, and I don't think it's going to happen actually.
That would be a lot more complicated.
And I don't think it's happening because my impression is that the particles in the system never really are coupled to like the shift in the potential that's occasioned by their motions. Like they don't know that they're changing the potential. I'm guessing. I'm not a PME expert by any means. I'm not at all. But that should be testable.
Yeah, I'm not a PME expert either, but since the same calculation is being used to compute, since the same formalism is being used to compute both energies and forces, I would assume that if it affects energies, that it also affects forces, but I couldn't tell you for sure.
Yeah, the reason why it might not has to do with just how it's basically, it's almost like you have to do the chain rule. You have to do the chain rule to find out how the motions affect the and if that somehow if that's not effectively being done, then it won't manifest. But anyway, so great. Okay, this is good. So
okay, so we'll continue. Okay, so these are the four different effects that I just went over. Three of them caused by these offsetting potentials, and the final one caused by the fact that you only have a finite amount of solvent in your periodic system. So I just want to give like a high level mathematical summary of what goes into each of these offsets. So for example, the offset caused by the net charge of the solute depends on so Q1 is your solute's net charge, for example, in the final state of your FEP calculation, and Q0 would be the net charge of your solute in the initial state. And in this case, you have Q worth of potential also being felt by Q worth of charge. So you have an overall Q squared dependence, and it's also a function of the size of your box. So L in this case would be the length of the periodic unit cell, and there's a whole bunch of constants and unit conversion things that go into the actual correction, but it's basically a function of the squared charge and the length of the box.
Why is it squared?
Because let's say you have your ion in the box. The ion is creating, let's say the solvation energy of your ion or your charged ligand is what you're interested in, and it's changing from Q0 to Q1. So that ion is creating some Q worth of average potential in the box, and it's also feeling that Q worth of average potential in the box. So it becomes Q squared. Okay. The offset caused by the offset from the
but then what you're talking about is an energy, not a potential.
Right, is an energy.
Okay,
yeah, that's right. Right. These are the corrections that you apply to, for example, your solvation free energy or your binding free energy. So yeah, you're right. Maybe the slide is misleading because it says phi offset, but what I actually mean is the free energy that results from that particular correction term. And then then there's the potential offset caused by the isotropic quadrupoles inside all the solvent molecules. Is just going to be a function of the Q of your ligand over the volume of the box. Then there's this. Then there's the residual.
Why does it charge the ligand like the solvent?
It's the charge of your ligand is feeling the solvent.
Oh, I gotcha. Yeah, thanks.
Yeah. Yeah, sorry, I should probably rewrite this slide to clarify that these are all free energies. Then, again, you have the charge in your ligand, which is feeling the effects of the residual integrated potential caused by, for example, the protein or any other strange solutes in your system. And then finally, there's the undersolvation term, which is, again, a Q squared term over the length of your box. So in the paper and later in the talk, I'll show you each of these in a little bit more detail. Okay, so what did we actually simulate, and why do we actually think that our results are valid? So the model system that we used to study this problem is this protein, which happens to be cytochrome C peroxidase. It's a cavity mutant. So charged ligands combined it's a tryptophan. A tryptophan which becomes positively charged as a radical is mutated out of the protein and replaced with a glycine, which opens a cavity pocket where positively charged ligands will bind. So in addition to the JChem Phys paper that we're talking about, we also did a study of actually trying to make blind predictions of ligand binding to this system that if you're interested in the subject, I would encourage everyone to read. It has a long supplemental talking about finite size effects, which is been superseded by the J-chem paper. So, so don't look too hard at the supplemental. But the results on binding free energies are still very interesting, especially for what they say about force fields. That was a digression. Okay, so we have cytochrome C peroxidase here, and what I've drawn in red and blue is something that we did to this system just to demonstrate an extreme case of what we were talking about. So I told you how how proteins can create some perturbation to the average potential in the unit cell, and that's true. But just to make a really extreme case, we created a version of this protein where the red atom here, drawn at the center of that sphere. So first of all, this is a stereo image, so you can, if you're far enough away from the screen, you can look at this in 3D. That red atom, we gave it an enormous negative charge of -80, and then all the blue atoms in a sphere around the red atom, we gave compensating positive charges that added up to +80. So this sphere of the red atom and blue atoms basically create an enormous isotropic quadrupole in the system, perturbing the average potential, creating an offsetting potential, and one of the results that we'll show is how this affects the free energy of charging up that ligand that's far away from that isotropic quadrupole. We didn't do this on every system, but it's just one of the demonstrations that we did in the paper. So all simulations were done in explicit solvent with all the coordinates of the protein fixed in space. So the protein is treated completely rigidly. It just made the convergence of the calculations much easier, so we could clearly separate the effects of finite size artifacts in this system from effects of converging to the right free energy or anything else. Any questions here? Okay. So we made 8 different versions of this, well, 7 different versions of this system, as well as one system that's just the ligand by itself. The different versions of the protein, we created different versions of the protein that were kind of the equivalent of different protonation states, like different pH versions of the protein. So in the first column, QP is the charge on the protein. So we simulated this protein with different net charges between -5 and 0 and 3, up to a version of the protein that had a net charge of 9. And then we also took the charge 9 version of the protein and created that isotropic quadrupole on it that I was showing on the previous slide, which is what I call net 9 quad. And then we also did 2 versions of this system where the net charge on the protein was compensated by an ionic strength that had some excess ions to get an overall net charge on the protein plus the ions as 0. So that's what we call net -5 ion and net 9 ion at the bottom there. And then for each one of these systems, we simulated it in cubic boxes with sizes between 7.5 nanometers and 11 nanometers. So we calculated the free energy of charging up this ligand using each of these different charged isoforms of the protein at a range of different periodic box sizes.
You said this, what was the charge you put on the ligand? What was the charge you put on?
The ligand has a charge of +1.
Okay.
Okay, so these are the charging free energies of the ligand with respect to the box size that it was simulated at. And you can see, first of all, that in each different case, the charging free energy varies by several kilojoules, up to like tens of kilojoules, depending on the box size that the system was simulated at. And it doesn't even change in a consistent direction. So for some of the systems, the free energy becomes less negative as the box gets larger. For some of the systems, the free energy gets more negative. Well, I guess that's, yeah, for the net -5 and for the net 9 quad, the free energy gets more negative as the box size gets larger, and the slopes are all different from each other. So basically, every different system behaved differently, and the free energy of charging the ligand was always, or varied by some amount at different box sizes. So now we wanted to use this understanding to correct these different free energies and figure out what the free energy would be for each different system in an infinite non-periodic box. So we designed two different correction schemes to correct for these effects, and we called one the numerical correction scheme and the other the analytical correction scheme. So on the previous slide, or on the earlier slide, I described these four different things that affect the charging free energy, the three offsetting potentials, and the undersolvation. And in the numerical scheme, all four of these different terms are basically calculated together. And the idea behind the numerical scheme is very simple. You want to know the difference between your free energy in a periodic system and your free energy in a non-periodic system. So you just recreate your MD system in a Poisson-Boltzmann calculation. You recreate your MD system as a periodic boundary Poisson-Boltzmann system, calculate your charging energy, and then calculate your charging energy in that same system in a non-periodic system, and take the difference between the two. And the fact that you've moved from your MD system to your continuum solvent PV system means that you can, you can't model the infinite solvent, the infinite system without using continuum solvent. So we move to continuum solvent. You calculate what the charging energy is for your periodic system. You calculate what it is for your non-periodic system, and then even though you were using continuum solvent for that calculation, you assume that the difference between those would be the same difference you would get in your MD system, even though it was computed under continuum solvent. So
You assume what?
So you can't model your infinite non-periodic system used in MD with explicit water molecules. So to model the infinite non-periodic system, we switch everything to continuum solvent, and then take the difference between the non-periodic system and the periodic system under continuum solvent, and then use that difference to correct the result that you got from your MD simulation in explicit solvent.
You have to do it for each charge lambda, in fact, or
Sorry, I couldn't hear the question.
you have to do it for each, charge lambda each step in the charging process, or you can do it once and get what you need from that.
I think you could do it once, once for the overall calculation.
Okay. And
And then another question is like how configuration dependent is what you get out from the PV, is this difference that you get in your PV calculation, and I guess it depends on how much your configurations vary. I think for simulating binding to a protein where the protein doesn't like dramatically change conformation upon binding, I think you could probably use just one configuration. And in general, the magnitude of this correction is not going to be huge. So because the magnitude isn't huge already, it's probably not a big enough. It's not a large enough source of error, the difference from configuration to configuration.
could you just go back to your slide with the size variation graphs for the?
Yeah.
Okay. So I guess I'm wondering, have you sort of, the system was set up to really manifest these effects with a plus and minus 80, right?
Well, the plus and minus 80 is only present in the net 9 quad line, the pink line.
Oh, it's only
All the others are just generic protein pulse field.
let's see.
The one thing that the that that is actually the the effects are exaggerated in the cases that do not have neutralized proteins. So if you look at three of these curves, the top one, which is net 9 ion in purple,
Yeah.
and the net -5 ion at the bottom in light blue, and also the net 0, you'll see that they all look pretty similar.
Uh,
They're still changing by I don't know, like 5 kilojoules over that range of boxes. Um, but you know, they're not changing as dramatically as the others. And the reason that and so this is what this amount of change is what you would expect um, in a simulation where you neutralize your protein with ions, and which is, like, you know, the most typical simulation case.
uh,
But actually, I should say that obviously, I should say that different proteins will look different because, you know, your protein of interest might have some ridiculous isotropic quadrupole when you actually try calculating it. So I guess I can't give a general guideline like, you know, this will be small. You don't have to worry about it. Plus, the thing is, you know, you spend a year doing all your figuring out your problem and doing all your simulations and calculating your binding affinities, and all these corrections you can apply in a day. So because it's not difficult to correct your results for this effect, and then you'll know for sure what would my results have been in an infinite non-periodic system that I can compare to any other people simulating the system. I think it's always worth it to correct these effects, even if they're not, even if they don't happen to be, even if they don't turn out to be large in magnitude. Okay, so what I was saying was that the way the numerical calculation works is you switch to continuum solvent, you calculate your charging free energy in a periodic continuum solvent calculation and a non-periodic continuum solvent calculation. You take that difference, and that is your correction, which corrects for all of these effects at the same time. The one caveat there is that it doesn't include a correction for the isotropic quadrupoles that inside the water molecules, which is what I call delta delta G DSC, which stands for discrete solvent correction. But there's, you know, a very simple formula in the paper that corrects for that. So you have to do one other thing besides just do these two continuum calculations. The downside to this numerical scheme is that you need a PB solver that can do the periodic boundary PME calculation, and that doesn't in like common PB solvers like APBS, for example, you can't do a periodic boundary PB calculation. So you need to. So I don't actually. So for our paper, we used Philippe Hunenberger's custom PB solver that I don't think is distributed, and I don't know which other PB solver can do periodic boundary calculations. Someone told me that the Charm program will do that, but I haven't confirmed it myself. But more to the point, you don't actually need to use this numerical scheme because the analytical scheme is great also. So in the analytical scheme, you actually calculate a separate correction for which is all analytical for each of these 4 different effects, and the formulas for each of these are given in the paper. But the one caveat to the analytical scheme is this residual integrated potential correction. So we call it analytical because the dependence on the box size is entirely analytical, but you still need to do a numerical calculation to figure out what the residual integrated potential of your particular protein is. This is the part that will vary from one protein to another. But once you calculate that residual integrated potential for your protein, you could then take that same quantity and use it to correct any of your simulations, regardless of what box size you've simulated them under. Whereas in the numerical correction, if you want to switch to a different box size, you have to recompute, you have to redo your periodic boundary calculation at your new box size. You can't just extrapolate to what things would be under a different box size. Whereas in the analytical system, using the analytical corrections, once you've calculated this residual integrated potential, you just plug in a different box size into all these different formulas, and you get your different result. Okay, hold on. I'm just going to get a glass of water. Okay, so just a little bit more detail on what these different formulas look like. This is the actual formula for the net charge correction given in the paper. There are some constants out front, and then the squared net charge of the system. So if you imagine that you're charging your ligand from charge 0 to some final charge QL, then you have that final net charge in the system minus that initial net charge in the system times 1 over L. Then there's also the offset from the solvent. No, actually, then why is this slide not advancing? There we go. The undersolvation correction at the bottom actually ends up having the exact same form as the net charge correction, just with this term of 1 minus 1 over the dielectric constant, or the solvent dielectric out front. So these terms actually basically end up canceling each other out, just leaving a factor of 1 over the solvent epsilon. Then there's the offset potential from the solvent, which has some constants, as well as, and then ultimately depends on the number of solvent molecules, which is that NS divided by the volume. So number of solvent molecules divided by the volume is basically the density of the solvent, and then the term on the left is how much each individual solvent molecule is contributing to the average potential in the unit cell, which is easy to calculate. And then finally, there's that caused by the protein's residual integrated potential. So again, this is like a final minus initial type of formula, where the final, once your ligand has been fully charged, is you have two residual integrated potentials. IP is the protein's residual integrated potential. IL is the ligand's residual integrated potential interacting with the charge on the net charge on the protein and the net charge on the ligand. So that's your final, and then your initial before the ligand was charged is just the protein's residual integrated potential interacting with the protein's charge. So this is easy to calculate once you have calculated these residual integrated potential terms, the IP and the IL, and that's what you actually have to do your PB calculation to calculate. But the nice thing is you can do that PB calculation with any PB solver, because it's calculated under an infinite non-periodic system. So you don't need a fancy PB solver that can do periodic boundary calculations. You just calculate IP and IL using your run-of-the-mill PB solver, and then plug it into the formula, and then you have your free energy correction term that applies to your binding calculation. So you add up all of these, and now you have converted your binding free energy, or you've converted your charging free energy computed under periodic boundary conditions to what that charging free energy would have been in an infinite non-periodic system.
Nathan is trying to ask what the gamma is in the discrete solvent term.
The gamma in the discrete solvent term is the quadrupole trace of the solvent molecule, which is easy to calculate from the topology of the solvent molecule. So like tip 3P will have a different gamma S from SPC water or whatever other water molecule, whatever other water model. But if you know the parameters of your water model, like the charges and the distance, then you can calculate that gamma S.
What's actually the eta LS?
Yeah, that is the Wigner constant for lattice sum calculations. And I don't actually know how it is calculated, but for a cubic box, it has a value of about it's either minus 2.7 or positive 2.7. But the definition is in the paper, and there is probably some decades-old reference where it is first that shows what it actually is. I'm not sure offhand how to calculate it numerically.
So just to confirm, so if we use non-cubic box, then we need different number, different value.
Yeah, that's a good question. I don't know exactly how this would change in a non-cubic box. I have found. Okay, so you're right that I think that LS term, that LS constant should actually be different in a cubic box versus a non-cubic box. But I have found that if you take a non-cubic box like these dodecahedral boxes or whatever is common in MD, and you compute its total volume, and then from that volume you take the cube root of the volume to get like the length of a cubic box that corresponds to the same volume as your non-cubic box, and then plug it in to the equation using the constant for a cubic box, that it matches pretty well.
Okay.
So I don't know if that's you may want to confirm that for yourself. I haven't looked at it in a long time. But so at the end of the paper, we actually give some suggestions for how to extrapolate this work to non-cubic boxes. But I don't remember offhand what those are.
Dave, this is Mike.
Yes.
The first expression is solute net charge. So if your simulation as a whole, if you're not doing a charging simulation and whatever you do keeps the net charge inside the box 0 through counter ions or whatever, does that first term go away entirely? Does the offset from the solute net charge go away entirely?
Yeah. If the net charge of your system, so all of these free energies are the what you would correct for free energies if you were charging up a ligand from some initial charge to some final charge. However, let's say imagine that you inserted 2 charges at the same time at different places in the system. Even though this net charge term, the delta G net, would cancel out, I am concerned that the other terms, like the delta G rip, would not cancel out because it does depend on the configuration and like the position of where your charges are. So I haven't investigated the full consequences of that, but I'm worried that you will see finite size artifacts even in situations where you never change the neutrality of your system, because of the position dependence of some of these terms. and Benoit Roux has looked at this a little bit, and I think he found about in one particular system that he was looking at, he found about a 1 kcal per mole difference between doing his PMF in a periodic system versus doing his PMF in a non-periodic system, even though the net charge was always 0. And then there was a little bit of a difference of interpretation, like whether 1 kcal per mole was high or whether 1 kcal per mole was low, whether it was negligible or not. But he did see an effect, which is consistent with what I would expect. But anyway, you're right that if the net charge of your system is always 0, then the top term, the delta delta G net, is going to be 0. Sorry, I can't hear.
If your result depends on where the charges are, that implies a position dependence, but going back to Mike's earlier question about forces, you would think it might affect the forces as well.
Yeah, then we loop back to that. So the delta delta G rip does depend on position, and that's why I'm worried. And I'll hopefully give you some intuition on why that is a little bit farther along. Shall I continue?
Yes, thanks.
Okay. Okay. So I just want to say one more thing about these residual integrated potentials and how you calculate them. So you calculate them using non-periodic Poisson-Boltzmann calculations. So just to go back to the very beginning, I said that in a non-periodic calculation, the potential at infinity is 0, whereas in a periodic calculation, the average potential is 0. So we're trying to figure out what the effect of your protein or other strange solutes is on the average potential in the system, and the idea behind what we're doing here, the idea here is that the protein far away from the protein's effect on the average potential is just okay. Far away from the protein, the only way the protein affects the average potential in the system is due to its net charge. Its charge configuration doesn't affect the average potential in the system, far away from it. So therefore if we model everything far away from the protein as a continuum, we can get how the protein or whatever solutes affect the average potential in the system by taking the difference between what we're calling a reference system and a real system. Okay, so let's just look at the sorry, give me 1 second. Yeah. Okay. So just looking at the left side of this, let's imagine that you have your ligand, which is small. Oh, sorry. I'm getting a message that I need to ignore. Okay. So there is some residual integrated potential caused by the ligand, which is what's being shown on the left, and there's some residual integrated potential caused by the protein, which is what's shown on the right. So imagine that your ligand were just a point charge, then that would create some potential, and that's what's being shown in the top left box. But the ligand isn't just a point charge. It has some charge distribution, and it has some excluded volume. And that's what's being shown on the bottom. So the top is just the ligand's net charge at a point, and the bottom is the ligand's actual charge distribution and the fact that it's excluding solvent away from itself. So if you create the top system in a PV calculation and and uh, and calculate the integrated potential over the entire volume of that PV system, and then you create the bottom system in a PV calculation and calculate the integrated potential everywhere, or the actual value of that potential, at the outer boundaries of the system is going to be basically the same, and it's only going to vary in the area nearby the ligand. And the assumption is that that difference between the that difference between a periodic system and a non-periodic system, that difference between the real system drawn on the bottom and the reference system drawn on the top is going to be essentially the same whether you have a periodic calculation or a non-periodic calculation. So you can calculate it under a non-periodic system and it will still apply to a periodic system. Okay, sorry, I probably explained that terribly. The point of the residual integrated potential is how does the fact that you have the actual spatial distribution of the charges on the ligand as well as its excluded volume, how is that changing the average potential in the unit cell? Just in the same way that the fact that your water molecule has a negative charge at the center and some positive charge on the outside is changing the average potential in the unit cell. The ligand's charge distribution is also changing the average potential in the unit cell. The way to compute that change is to compare the average potential to what it would be if the ligand were just a point charge with its total net charge. So that comparison is calculating the integrated potential in the bottom system and subtracting the integrated potential in the top system.
Okay.
Yes.
Could you sort of get them both at the same time by doing the bottom system calculations with periodic boundary conditions and without periodic boundary conditions and subtracting?
You mean the left and the right at the same time?
Well, I guess what I'm saying is the bottom is referenced to the top, right? And the top one you did with periodic boundary conditions. You got that correct?
No, none of these are done with periodic boundaries.
No, but previously, in your prior, like there's a prior correction, I forget what it was called. Maybe it was a net charge correction that you got with periodic boundary conditions. Right?
You mean...
So you've got that with periodic boundary conditions, now you're going to do this with non-periodic, but couldn't you go straight to the full representation of the protein and ligand and do those with periodic boundary conditions and just get everything at once?
So that idea of getting everything at once is, that idea of getting everything at once is basically what the numerical correction is. The nice thing about doing things separately is that the different things have different, you could if you want physical intuition about what's going on, you can say that the different things have different physical origins, and on top of that, they have different size dependencies. So the nice thing about breaking out the net charge correction from the residual integrated potential correction is that first you understand the physical origins of each differently, and second, if you go to some different box size, you can use the quantities that you've already calculated and just compute what they would be at the new box size. So I separate the net under this analytical framework. I separate the net charge term from the residual integrated potential term because they have different physical explanations and they have different dependencies on the box size. But you're absolutely right that you could calculate everything all at once, which is the premise of the numerical correction.
Okay, thank you.
Okay. So sorry, just to explain this badly one more time. What is being computed here is the difference in total potential in this non-periodic system between the actual system, which has some excluded volume and has some charge distribution, and this reference system, which is just the net charge completely surrounded by solvent. and you can compute this using whatever PV solver you want. We suggest doing it with APBS, and in the supplementary material of the paper, I give a sample, an example APBS input file, and also a Python script that takes the output of APBS and calculates what this residual integrated potential is. You at least if the math in the paper is unclear, then you could look and see exactly what the Python script is doing, or vice versa, I guess. If you have never done PV calculations, you can take the example input script and the Python script and get out what you can recreate the residual integrated potential values published in the paper from the protein topology and see that they match up, and you can run it on whatever your protein is and see this is what it is. So I just wanted to say that the magnitude of this quantity is it's idiosyncratic to the particular protein, and it's not always intuitive. So for example, these are the actual magnitudes of the integrated potentials, of the residual integrated potentials in each of these different systems, and they're all over the map. I mean, yes, the net9 quad, where we added this enormous quadrupole, has the largest magnitude residual integrated potential by far. But actually, if you look at the net zero is just our run-of-the-mill protein parameterized with amber, and it has a larger residual integrated potential than the protein that happens to have a net charge of 9. So there's a consistent trend going from net -5 to net 0 to net 3 to net 9, but it's not like it's correlated with the net charge of the protein. Well, it's not like the magnitude is correlated with the magnitude of the net charge of the protein. So I expect that some different looking protein would be different, and I don't know what that would be. But it's easy to calculate because we give you the APBS input file and we give you the Python script. So run it on your protein or your host system, your host guest system, and see what it comes out to be. Okay. So what happens when you apply these corrections? So the left are the uncorrected charging free energies, and the right are the corrected charging free energies. The lines show the analytical estimate. No, the lines show the numerical estimate, and the crosses show the analytical estimate. So whether you do it all at once using a periodic boundary PV calculation, or you break it out into each of these individual terms, you basically get the same correction, and all these lines flatten out substantially. But you'll notice that they don't become totally flat, and that's because, in both of these cases, we're doing some kind of approximate PV calculation, which has some parameters like how do you define the dielectric boundary, and the dielectric boundary isn't a real thing. So all these are going to depend a little bit on how that dielectric boundary is defined. But what you can see is that you can take these corrections that were computed using just the equations plus a little bit of Poisson-Boltzmann, and use that to correct MD results in explicit solvent, and get charging free energies that are much less dependent on the box size that was used. And keep in mind, like, we don't expect all these systems to give the same answer. Like, they're all completely different isoforms of the protein that would have different charging free energies. We just would expect that the size dependence would go away. So this shows the effect of that dielectric boundary. So in the top figure this shows what actual charging free energies we get for each definition of the solvent radius that's used to define the dielectric boundary for the calculations. So once your solvent radius is about an angstrom, then the charging free energies really stop changing, and the bottom is the slopes of all of the charging free energies with respect to the box size. So we would expect that once we found the right PD parameter, that once we found the right solvent radius for our PV calculations, then the slopes of these previous plots would go to 0, because with the right parameter, you would no longer see any dependence on the box size. And you can see that if you define your dielectric boundary with too small solvent radius, then you still see big slopes. But right around 1 angstrom, all the slopes for each of these systems get pretty close to 0. So it seems like an ideal solvent radius to define the dielectric boundary for the PV parts of the corrections is about 1 angstrom. And if you look at what that actually looks like, now you see much flatter curves that are still not completely flat, but now the size dependence has been greatly reduced. So this is our evidence that the corrections are useful. Okay. So just to look at the question.
Could you just go back again?
Yeah.
If somebody from, I can't see the slide because somebody, oh, there we go.
Wait, what?
No, it's okay. So B and C.
B is using like a conventional PV solvent, a conventional dielectric boundary of like 1.4 angstroms or something, and C is using a definition of the dielectric boundary that was optimized to make these as flat as possible.
The one in the middle is 1.4. What's the one B and C? What's the difference? It's different.
The difference between B and C is the definition of the solvent radius in the PV calculations that were used to compute the correction terms.
Yeah, do you remember the numbers? Just out of curiosity.
I'm sorry?
Do you remember what radii were actually used for that?
I think B is 1.4 angstrom and C is 1 angstrom.
Got it. Okay, thank you.
Yeah, okay. Okay, so this shows the 8 different systems and the magnitudes of each of these different correction terms. So we combined the net charge and undersolvation terms as the black line, because a while ago I said that they basically cancel each other out, leaving just a factor of 1 over. Because in a high dielectric solvent, those terms basically cancel each other out. So the black line is not very large. The main thing to see here is that in all of these systems, the largest contribution to size dependence is the blue line, which is the discrete solvent. I forget what the F stands for, but it's the size-dependent part of the discrete solvent correction. Basically, so the discrete solvent correction is the effect of that isotropic quadrupole inside the water molecule. You know, that the water molecule contributes some negative potential to the system. If your system were infinitely large, then for 2 different systems, this correction is only going to be different if those 2 systems have different densities of water, right? So in a very small system where your system is mostly protein, the overall density of the water in terms of number of water molecules per volume, per the entire box volume. In a smaller system, your protein is a relatively larger fraction of the box volume. And in a larger system, your protein is a relatively smaller fraction of the box volume. So the blue line is the effect of the fraction of water in your system changing in these different systems. And that's actually the biggest contribution to size dependence in almost all of these systems. You can see that in the systems that are neutralized, like net 5 ion and net 9 ion and net 0, almost all of the other terms are very small, except for this change in water density term. So basically, if you have not neutralized your system, then the other terms will be very large, like in net 9 or net 9 quad. But if you have neutralized your system, then the other terms besides this change in water density term are probably going to be small. Unless your protein happens to have some completely crazy residual integrated potential. I don't know what protein that would be.
So the DSF, delta T DSF term comes from the water isotropic quadrupole, is that what you mean?
Yes. So we're using three different acronyms for this, and we actually have a legitimate reason to. DSC is the term that we used for discrete solvent correction, which is caused by that average potential created by the water molecules. We split that term out into what would it be in an infinite system, because if your system were super large but still periodic, that term never goes away, but it does converge to a constant. It converges to a constant because once your system is 99.99999% water and everything else has basically gone away, then as you change the volume of your system, the density in terms of water molecules per volume is no longer changing. So that constant we called delta delta G DSI, which is listed there as what it is. And then the DSF term is the fact that your system is not actually basically entirely water. So that blue lines you can see are converging to 0 as the system gets larger, because once your system is basically entirely water, then we know what the discrete solvent correction is, which is delta delta G DSI. And this is actually kind of important because if you do a typical ligand charging calculation where you want to calculate a binding affinity, so you charge up your ligand in the protein system and you charge up your ligand in a water-only system to see what the binding free energy is going from the solvent-only system to the protein system. Those two systems have different overall densities of water, different numbers of water molecules per volume. So this term won't actually cancel between those two legs of your thermodynamic cycle. So it's important to include in correcting your binding free energy results. Okay. So to try to summarize everything, charging calculations in periodic systems suffer from noticeable artifacts due to periodicity. You can correct these artifacts using analytical corrections, but to compute the residual integrated potentials, you have to do a simple PV calculation. We suggest using APDS with our input file and script. The artifacts are largest when the system net charge is large, or the ligand charge is large. And if you've neutralized your system with counterions, then most of the terms become pretty small, except for that solvent term. And finally, I suspect that even PMF calculations or simultaneous counter-ion uncharging will suffer from these artifacts, and this is because that residual energy potential correction actually can depend on the geometry of your system. But this is not something that we investigated in a lot of detail. So I'm happy to take any questions that you have right now. And thanks for listening. And please read the paper. I'm sure that after this presentation, you don't think this presentation was not sufficient to understand everything in full detail, but hopefully it'll make the paper easier to understand.
Yeah, it was really helpful. Really helpful. I really appreciate it.
Yeah, well, thank you for listening. Any questions here, or are we all done? All right. Well, thank you, everyone.
Thanks, Gabe.
Yep.
Yeah, thanks so much, James. Thank you.
Yeah, thank you very much. It was very clear.
Okay, thank you. Yeah, have a good Tuesday. Email me if you have any questions.
Okay.
All right.
Talk to you later.
Yep, bye, everyone.
Okay, folks, thanks. Bye.